Okay, welcome back to part 2 of this lecture on the chain rule. So the next theorem here is going to be just a nice application of the chain rule. So let me make sure this is focused. And so here we go. So there's kind of two parts to it. So let's go ahead and assume that let u be a differentiable function of x. Okay, so we'll start with that. And the first part, we don't need that, but so the derivative of the natural log of x, okay, is equal to 1 over x. So that one doesn't involve u, and this is of course where x is greater than 0. And the second one, however, is going to be where we allow x to be something other than just x, where we allow it to be a function itself. So d dx of the natural log of u. Well, so that one we're going to use 1 over u times du dx, which ultimately you could write as, so this is just u prime here, so it's 1 over u times u prime, or better off u prime over u. And this is of course where u is greater than 0. So the argument here of a natural log function has to be greater than 0. Okay, so very simple, right? So this one here, I mean, you can just prove it just by using this fact together with the chain rule. Okay, so that's very simple. Let's use this to calculate some derivatives. Let's look at some examples here. So what about, just to start off simple, y equals the natural log of 2x. Okay, so in this case, so dy dx here is, well, we know the form, right? This is the natural log of u, right? This is basically what we just talked about. So this is going to be some u prime over u. You got to figure out what u is. So what is u here? Well, u is 2x, isn't it? Right, so we can just plug it into this form. So u prime would be 2, and then u is 2x. So in this case, the derivative is just 1 over x. All right. What about, let's up the ante a little bit here. What about the natural log of x squared plus 1? Well, in this case, u is equal to x squared plus 1, right? So again, just using that format, the form that we just talked about, u prime over u, right? So we can see that the derivative of this is 2x, and then u is just x squared plus 1. Okay, so really quick, easy derivatives to calculate. And how about something else here? What about this one? This one is a little more involved. Y equals the natural log of x all to the third power. So here we've got kind of a general power rule sort of thing happening. Right? So in this case, you'd have dy dx. Okay, so this is you can think of this as the general power rule, right? You've got natural log of x can be the u, and then you've got u cubed. So this would be like 3 times the natural log of x squared, but then I gotta, what do I have to differentiate that inside piece too, don't I? Yeah, so that inside piece, the derivative of natural log of x, that's the one we just talked about. It's 1 over x, right? So this would be 3 ln x times 1 over x. Sorry, this should be squared too. All right, and so we better write that better than that. This is 3 times the natural log of x squared over x. That may not be the best way to write it, but we'll leave it at that. Okay, all right. Very good, so there's that derivative. And so this is just, more differentiation rules. This one is kind of straightforward. This one, obviously involves the chain rule. And so you can just remember it as the chain rule if you like. I mean, I kind of like to just think of it as the chain rule. But if you want, some people do like just to remember the format u prime over u. That's also easy to remember. So okay. I find if there's just too many things to remember, then I kind of want to limit the number of things that I have to just straight memorize and instead just think of the reason that things are the way they are if I can. If it's easy to remember the reason. Reasons tend to be, sometimes the reason that something is true is very easy to retain, and it's almost like once you see it, you can't forget it. It's kind of like riding a bike. Like, I can't forget why that's true. Like the chain rule is one of those things where it's like it's hard for me to forget. It would be hard for me to forget that form. But then there are other things, of course, that are like seemingly more difficult to remember, right? So here's another example. This one, let's try to differentiate the function f of x equals the natural log of, and then here we're going to take the square root of x plus 1. Okay, so this one we're trying to be very tricky. So notice we can do some simplification on this function, right? Because straight away this looks pretty tricky. You've got the natural log of the square root of x plus 1. So let's use some facts about logarithms here. So this could be rewritten as the natural log of x plus 1 to the 1/2 power. And then if you recall, with logarithms, it's possible to take the exponent and bring it down into the front. So this would be best written as 1/2 ln of x plus 1. That's sort of an easier, somewhat more manageable way to write this. And so that 1/2, that square root basically just becomes a constant in front of the natural log. So then f prime of x would be equal to, well, I'm going to bring the 1/2 out front, and I'm just going to write it, ddx of ln x plus 1. Well, this is just the natural log of a u, right? The u here is x plus 1. So the form here is 1/2 of u prime over u, right? And so we just have to know what we want our u prime and our u to be. So in the case in the case of this function, the u is clearly just x plus 1, right? And so you've got 1/2 of, what's the derivative of u? Well, it's just 1. And what's u? It's just x plus 1. So it looks like that, doesn't it? So this would be, so then the f prime of x would be equal to 1 over 2 times x plus 1. That's your derivative in this case. Okay, so that one is, I mean, this could have been done without using the log trick, right? You would have to just use the chain rule inside the chain rule, right? Or the natural log rule inside the chain rule. That's fine too. Really, the natural log rule is just the chain rule. This is basically a double application of the chain rule. You get the same answer, right? But sometimes, if logarithms are in the expression, you can simplify. You can use some nice facts about logs. Okay, here's a very extremely messy example that benefits dramatically from some cleanup. So here we'll say y equals the natural log of a big old mess here. So it's going to be x times x squared plus 1 squared divided by the square root of 2x cubed minus 1. So it looks a bit like that. Now this one is again, you could differentiate this, I believe. You could use the chain rule inside of so you could use the ln rule, ln of u prime over u, and then to calculate u prime, you would have to use quotient rule together with the product rule, right? So you'd have to kind of use both, and then you'd also have to use chain rule, I believe, when you differentiate the low function. You can do it. It's just pretty involved. So what I'd like to do instead is show you that this could be simplified greatly, right? So remember, when you have the natural log like this of products and ratios, you can kind of break them up a bit, right? So in particular, this can be written as the natural log of x, okay, right? So the numerator here, you're going to add those two as the natural log, plus the natural log of x squared plus 1, and then this would be squared here, so instead we'll write the 2 up in front, right, like that. Okay, and then plus. Now, what you could do is you could bring this thing up into the top here and make it 2x cubed minus 1 all to the -1/2 power. So technically it'll be plus -1/2 natural log of 2x cubed minus 1. So it looks like this. So this function has alternative forms, and one of the forms is this form, which is much easier to work with than this form. Again, you could differentiate this straightforward. It would just require the chain rule, product rule, and quotient rule all together, which is not a problem. You can definitely do that, but if you remember that this is a natural log, and there are properties of the natural log that allow you to simplify the expression, write it differently, then technically speaking, this is probably much easier to deal with. Okay, so then y prime, all right, we're going to differentiate all of these pieces. So we're just going to kind of go through this and differentiate what we can and write down the next steps if we need next steps. So what's the derivative here? Well, natural log of x we know is just 1 over x. And what's the derivative here? Well, it's plus 2 times, and now this is the natural log of u, so it'll be u prime over u. So if u is x squared plus 1, then u prime is 2x, and then it would just be x squared plus 1 in the bottom. Okay, and then it'd be minus 1/2, and then again the same u prime over u rule here, right? So it'd be u prime over u, so the u prime would be 3 times 2, 6x squared, and then the u is 2x cubed minus 1. All right, so then that's all of the derivatives. Of course, you can clean this up a lot. And, you know, maybe we'll say 1 over x plus 4x over x squared plus 1 minus, and so the 2 and the 6 will cancel. So maybe we'll put a 3x squared up there and 2x cubed minus 1 at the bottom. That works. And so this might be a good spot to leave it in. All right, so very good. So that's a lot of natural log derivatives. So what happens, what about bases other than e? So when we talk about the natural log, we're talking about base e, like the natural base, right? What about bases other than e? So let's define some stuff here first to make sure that we've got some of the mechanisms in place here to talk about logarithms with alternative bases. So let's start with this. So if a is a positive real number, okay, and we'll say a is not equal to 1, and x is any real number, okay, then the exponential function to the base a, okay, denoted by a to the x, is defined by, okay, so it's defined by this: a to the x equals e to the natural log of a times x. Okay, so that's just kind of a simple thing here, right? So I mean, basically what this is showing is the relationship between a to the x and the natural exponential, right, and the natural logarithm. So a to the x is equal to e to the ln a times x. And so a lot of people will remember that if you take e and you exponentiate it with natural log, then you can sort of think of these two things as kind of dropping out, and then the a becoming the base. And that's kind of the way that a lot of people remember it, but technically this is the relationship that exists between these two. Okay, and so then this leads to the following. That's kind of another definition here. If a is a positive real number, a not equal to 1, and x is any positive real number, so up above x was any real number, here x is any positive real number, then the following. So here you'd have log base a of x. Okay, the log base a of x is equal to 1 over the natural log of a times the natural log of x. Okay, so these are the two sort of definitions that we need before we can talk about the derivative of function exponentials that are base other than e, and logarithms with bases other than e. Okay, other than the natural logarithm. So given these two, right, and we'll use these in a second, let's talk about what the derivatives of functions like these look like. Okay, so theorem, let's say let a be a positive real number. Okay, a not equal to 1, of course. And let n be a differentiable function of x. U be a differentiable function. Okay, and so the following is true. Okay, then, so the first one is the derivative of a to the x. Okay. Well, we're going to write these down, and we're going to prove a couple of them in a second. So it's natural log of a, and then times a to the x. Okay. The second one, so this is just the basic a is a constant raised to an exponent, right? So how do I differentiate that? Well, it's if you keep that part out of the picture, then it kind of looks like e to the x, except there's some scalar on the front, natural log of whatever a happens to be. So it's similar. And then d dx of a to the u, right? You can probably guess this is going to be similar. It'll be the natural log of a out front, that's a constant, times a to the u, right? So there's sort of the symmetry, but then because u is itself a function, times u prime. Okay, so I have to differentiate u, so it's a chain rule. Two more here. What about the log base a of x? Derivative of log base a of x. Well, 1 over the natural log of a times x. All right, so kind of similar to what we saw before, right? If you remember, the derivative of the natural log of x was just 1 over x. And so this is not base e, this is base a, so you have to incorporate the natural log of a as kind of this constant here to correct for that piece. And then finally, this one is log base a of u. Okay, instead of just x, this u is now a differentiable function of x. And so you can probably guess this will be similar, natural log of a, right, times u in the bottom, and then of course u prime. All right, so you can kind of think of this as u prime over u, but with a natural log of a. Yeah, maybe that's u prime over natural log of a times u. All right, so let's prove a couple of these theorems. We'll prove one, and we'll do this one, and then we'll do this one. The other ones are similar. They just would involve just that additional piece because u is a function, right? So you need the u prime and the u prime. So the harder part really is establishing 1 and 3, because then 2 and 4 is just a simple chain rule application. So for the first one, so the first proof we'll do is that d dx of a to the x is equal to natural log of a times a to the x. All right, so that's the one we'll start with. Okay, so So to prove this one, we want to kind of first note that a to the x is by definition what we just described is e to the ln a times x, right? So this changes everything. So this is kind of the key to identifying this derivative. So let's let u equal ln a of x. Right, so notice that this is kind of like that. The natural log of a is some number times x. Then y is equal e to the u, isn't it? Okay. And then this is just the chain rule. So d dx of a to the x, let's just write it all out, is equal to d dx of e to the ln a times x. Okay. And you can think of this, again, we're going to use the chain rule here, so this is going to be d, so this would be like d dy dx, dy du, right? So d du of e to the u times du dx, which would be d dx of ln a of x, like so. Okay, and this one is really easy, right? So the e to the u is just e to the u, the derivative. And then this one, what is the derivative of ln a times x? What is ln a? Right? Ln a is natural log of the number a. That's just a constant, so there's no variable there. So so that is just a constant times x, and so the derivative is just ln of a. Okay, and so you can see that instead of e to the u, we would want to plug back in our ln a of x, and like so. And then instead of e to the ln a of x, we'd want to write that in the more compact form. This is just a to the x. Okay, so there we go. So the derivative here is the natural log of a times a to the x, just an application of the chain rule. Okay, but it's an application of the chain rule, but you also have to remember this fact. It's very important. Which probably, if you've gone through the pre-calculus coursework, you've seen this, hopefully. So hopefully this isn't just totally left field. Now, what about the third item here? So in the third one, what we were looking at was the derivative of log base a of x. Okay, there we saw that was 1 over ln a times x. Okay, so let's try this one. So let's prove this one. So d dx of log base a of x. Okay, so rewriting this, okay, so this log base a of x is equal to, so this was, again, the definition we just looked at. This is 1 over the natural log of a times the natural log of x. All right, so that was the definition we just discussed. And so again, here, this is just a constant, so it can come outside. And the derivative is just of the natural log of x. And so you can see this is 1 over ln of a, and then the derivative of natural log of x is just 1 over x. And so you could write that as 1 over ln of a times x. Remember, that's the natural log of a. Okay, very good. So, kind of spinning around a bit on this, but natural logs with alternative bases, all kind of predictable derivatives. Let's do a few examples. So let's start with y equals 2 to the x power. Okay, so we want to find y prime, so that's going to be d dx of 2 to the x. which the form is just ln of a times a to the x. And so we can see this is just going to be the natural log of 2, which is some constant, times 2 to the x power. Okay. How about another example? Y equals 2 to the 3x. So similar, right? Obviously similar, but here it's not just x in the exponent, it's a u function. Okay, so again, y prime is d dx of 2 to the 3x. Okay, and so the form here would be the natural log of a times, let me write it down here. So we're looking for this form, natural log of a times a to the u times u prime. All right, so our u is obviously 3x. Okay, and our a is 2, so we can just plug all those things into this form. So the natural log of 2 times 2 to the 3x, and then times u prime, which again, if u is 3x, then u prime is 3. Okay, so it'd be 3 times the natural log of 2 times 2 to the 3x power. Okay, no problem. And to finish out the lecture, let's do kind of a harder one here. Let's take one more example here, and let's make it a little more tricky. Y equals log base 10 of cosine of x. Log base 10 of cosine of x. All right, so the cosine here is what we're taking the log of, and it's base 10. Okay, not natural log. All right, well, so this fits the format of, so basically this here, because this is complicated, let's just write down what we're looking for. The ddx of log base a of u is what we're dealing with here. Right, in this case the u is the cosine of x, a is 10. Okay, and so we know that the derivative of this is supposed to look like this: 1 over ln of a times whatever u happens to be, and then u prime up top. So I really don't need that 1. So it's u prime over u, and then also ln of a in the denominator. Well, that's, I mean, when you see it like this, and you recognize that u is equal to cos x, this is pretty straightforward, easy to do. So y prime equals, well, if u is cosine of x, what's u prime? Negative sine of x. So we're going to have a negative sine of x in the denominator, or in the numerator. And natural log of a, well, if a is 10, then that's the natural log of just 10 in the denominator. And then what's u? It's cosine of x. So cosine of x needs to sit downstairs as well, just like so. So obviously this is a very complicated function, right? But because of this differentiation rule, it's kind of it's easy enough to identify what the derivative of the thing must be. Okay, so negative sine over cos. Now I guess you could write this as negative tangent, right? So maybe we want to revisit some of our trig days and write it like this. Okay, so same thing. Same deal, right? No problem. Okay, so that is where we'll end this lecture. Now next time, when we get into lecture 10, we'll be getting into something called implicit differentiation. So we'll start to modify the way we can think about derivatives and differentiation. And that'll sort of mark the beginning of kind of moving sort of away from just derivative rules and sort of moving into applications. I guess we've got a few. We're going to talk about implicit differentiation next time, and then after that we'll talk about derivatives of inverse functions, and then we're really going to jump into applying differentiation for really the rest of the course, the remaining lectures. So we're approaching the end of our sort of here's what the derivatives are, and then once we get past that, we'll be discussing now what can we do with them. Okay, so all right, I will leave it at that.